Hi friends, and welcome back to the Control Engineering Gig. In this video we're gonna learn how to draw Bode Plot using an example. We have this example here. This example, this G of A has one pole, 1 0 and 3 poles, and we need to know or draw the Bode plots or the frequency response of the system. First, we start by normalization and scaling. So to normalize a given transfer function, we factor out the pole or 0, and then scale out the frequency by assuming that the new frequency is equal to the original frequency as a ratio between the original frequency and the factor out pole or 0. Let's apply this on our transfer function. So we have to factor out this 0, this pole, and this pole. So it will be in this format, as you can see here. We further can simplify this transfer function into this form. So now we have it's fully normalized and scaled. The second portion or the second step is to draw the table. Okay, the table in the table you will consider the G of S as a part. You can know the slope, the breakaway frequency, the phase when it's when the frequency is close to 0 and when the frequency is close to infinity. You can watch a video with the link in the description to know how we can or how these values are done. Okay, so first let's start with the magnitude. The magnitude 3 by 2. It doesn't have a slope or break frequency, and it doesn't contribute anything to the frequency as well, or to the phase as well. Let's start with the first pole or 0 here. This 0 will have a slope of plus 20, breakaway frequency 3. It will contribute 0 degrees for the phase plot at low frequency and plus 90 at high frequency. The pole at the origin will have a slope of minus 20 decibel per decade. It has no breakout frequency, and it will contribute minus 90 for all frequencies on the phase plot. The second pole will have the same slope, but it has a breakout frequency at 1. It will have a 0 contribution at the phase for low frequency versus minus 90 at high frequencies. The second pole will have minus 20 decibel per decade with a break frequency of 2 and contribute same contribution as done by the previous pole. You can sum up these values here, which helps you later in the phase plot. So the phase plot, we know it will start at minus 90 and ends up at minus 180. Okay. One last thing we need to know is the beginning of the plot. This is done by substituting a small value of the frequency, like 0.1 or 0.01 frequency in the given transfer function. Okay, and do the computation and some approximation and assumption, so you can know roughly when to start the plot. So here we substitute 0.1 instead of every S or Laplace variable, then in compare with the pole or 0, we can cancel out these values here. Okay, so just zeros now, so we end up with 15k. K is the gain given in the transfer function. So the k here doesn't affect the phase, but it will affect the magnitude. So if we have k, positive k, it will push up the magnitude by its value, and when it has a negative k, it will pull down the magnitude by minus k. So it doesn't affect the phase plot, but it affects the magnitude plot. So if we assume k equal to 1 and take the logarithm of the 15, so our system starts with 23.5 decibel when the frequency is 0.1 radian per second. Okay. Okay, so we have all the information now. We can start plotting the magnitude part. So the magnitude part, you will have this log axis. So let's start with the first part in the system. One thing I have to mention here, always in this table start with the breakaway frequency. So the first breakaway frequency, we have 1 over s. It doesn't have any breakaway frequency. Combine this value with the magnitude and start drawing that, and then start with the smallest break frequency and work your out away to the largest breakaway frequency. So let's start with the first one, which is 3 by 2s. We know it starts from 23.5 with an angle or with a slope of minus 20 decibel per decade, because we have a pole at the origin. So how we can draw the slope here? It's very easy. You take, since the slope is minus 20, so take from minus 20 for 1 decade. This is 1 decade here. Okay, and you can complete the triangle here. So this line, the black line, will be your slope. So make this as a reference for you to draw the red line. Okay, let's go to the second break frequency, which comes from the pole at 1. So if you watch the previous video with the link shown in the description, you know the magnitude start from 0 until the break frequency, which is 1 here, and then decade angle line with a slope of minus 20 decibel per decade. For the second pole, it's also start from 0 until 2, okay, until 2, and will have a slope after that of minus 20 decibel per decade as well. For the last break frequency, which we have which comes from the 0, we have at 3. So it also starts from 0 until 3, break frequency 3, but it will go up because it will have a magnitude, a slope of plus 20. So what we need to do now is to summing up these. As you know, we have 3 duration or portion here according to the break frequencies. We have break frequency at 1, 2, and 3. So by that, break down the plot here based on the break frequencies. So the first portion here, it comes from the red line, the 3 by 2s comes from here, because all the values here are 0 for the other poles and zeros. So it will have the same part here until it reaches the 1 radian per second, or the first break frequency. After that, of course, this will have a slope of minus 20. After that, if you observe the system here, the blue line, which comes from the pole at 1, okay, contributes another minus 20 decibel per decade. So we will have a slope of minus 40. When we reach 2, you can see that the orange line, which comes from the second pole, also contributes another minus 20. So we will have minus 60. And after that, after 2 radian per second, the 0 starts to take away 20 decibel per decade from the slope. Okay, so now we will end up with minus 40 decibel per decade. This is how you draw the individual Bode plot magnitude for the poles and zeros, and then summing them up. Okay, this is a comparison between our drawing, which is the red one, and the MATLAB drawing. See, there is some error, but the approximation is well enough. Okay, let's draw the first part. Also, begin with the log paper. Start with the poles and zeros. The magnitudes don't have any contribution on the phase plot. Okay, 1 over S will contribute just minus 90 degree at all frequencies. The first pole at minus 1 will contribute 0 degrees for low frequencies and minus 90 at high frequencies. We have a break frequency at 1, so divide this by 10, so it will be 0.1. This will be 1 decade before the break frequency, and multiply it by 10, we'll have 10. This is 1 decade after the break frequency. For the second part, minus 2, okay, it will have 0 contribution until 0.2 radian per second. So if we have 2 here, this is 2, so this will be 0.2, and this will be 20. So multiply by 10, it will be 20. Divide by 10, it will be 0.2, and you can draw this line. So the line starts from 0 until the 1 decade before the break frequency here, and then we'll have a slope of minus 45 per decade, 45 degrees per decade, until 20, and will continue at minus 90. For the slope, also follow the slope we draw for the very first line. You can imagine you have 1 decade here, you have 45 degree here, so 45 degrees, you can draw a line here and use it as a guidance for your slopes. We have one last slope that comes from the 0 at minus 3. So this will be 3 here. So 1 decade will be 0.3. 1 decade will be 3 here. So this is 30, and this is 0.3, and this point here is 3. So it will contribute 0 degrees until 0.3 radian per second. After that, we'll have a slope of plus 45 degree per decade until 1 decade after the break frequency, which is 30. Okay, according to these break frequencies here, we're gonna have six portions depending on the break frequencies. We have a decade before the break frequencies and 3 decades after the break frequencies. So let's start drawing. The first one, as you remember from the table, we said that it starts from minus 90 and it has to end up at minus 80. Okay, so why is minus 80? Because we have a contribution from 1 over s, a pole at the origin. Okay, it contributes minus 90 degree for all frequencies until 0.1. All frequencies or all angles here are 0. After that, you see the blue line that comes from the first pole will give a slope of minus 45 degree. After 0.2, between 0.2 and 3, the orange one that comes from the second pole will add up another 45 degrees per decade, will be active in this portion. Okay, so this is minus 90. If you see after 0.2, the black one also shares its action with the other lines here. So it's basically take away a degree, 45 degree from here. So it will be just minus 45 degrees. When we reach the 10, which is the 1 decade of after the break frequency for the pole at minus 1, so the blue one will contribute only minus 90. Okay, so the minus, so we have the orange and the black will cancel out each other. Okay, so it will be just a line here. After that, the orange one also dies out here, so the only one that takes part here is coming from the 0 at plus or minus 3. After that, this 0 will be constant at minus 90, plus 90, sorry, so it will be just one angle, one line at minus 180. This is how you draw the individual face and then sum them up. Okay, the geek is happy now because we're done with the plot, and will be impressed when we compare the plot against what MATLAB gives us. So see, this is not a very well approximation, but it gives you some idea about the frequency response when it comes for the phase portion. I hope this was helpful for you.